Hey, what's up, guys? So today we are going to talk about CMOS transistors, which are, almost like everywhere in the modern life, in the modern devices. Like if you have a smartphone, your laptop, probably every single integrated circuit chip inside that device has billions of CMOS transistors over there. So now the question is, so what are they? Now let's talk about it today. So CMOS transistors, right? So CMOS is a type of MOSFET. So what is MOSFET? So M stands for metal, and O stands for oxide, S stands for semiconductor, F stands for field, E stands for effect, T means transistor. So that's MOSFET, and we are going to introduce that. We're going to draw a picture about MOSFET and let you know how that works. So CMOS is a type of MOSFET. However, it's being composed in a complementary form to make up computer logic. So CMOS, so MOS here has the same meaning here, right? So C stands for complementary. So which means all these CMOS transistors in the logic gates are being composed in a symmetric form. If you have a P-type transistor on the top, you have an N-type transistor at the bottom to form that kind of logic. And we're going to introduce some simulations for PMOS and NMOS transistors and logic gates to try to practice how that works. However, these are the definition, the names for that one. So make sure you know what are they. So when people are talking about this, you know what these things are, because they are just super popular right now. Okay. So let's take a look at what is a MOSFET. What that look like. So here's an example. So a MOSFET is a physical device. It's super tiny. So right now, people can fabricate a single MOSFET in a nanometer level, right? So they are a 3D structured physical device inside the chip, and it looks like this. It's just like in a bulk, looks like in a bulk, right? So this is one MOSFET, for example. Of course, it's 3D. And there's a metal on the top in the middle, and there's another contact and the third one. So there are transistor, right? So it means like 3 terminals. So there are 3 terminals. You have a metal contact. This terminal is called drain. This terminal is called gate. This terminal is called source. Okay, and the definition here is the dimension between source and drain is the width of the transistor. Oh, now that's the length of the transistor. And here, this dimension, okay, is the width of the transistor. And you also have at the bottom of this bulky device, it's not bulky, but bulky device, you have a metal contact at the bottom and have a wire connect to that metal contact. it's called a body contact. And if this MOSFET, so there are two types of MOSFET, a mainstream MOSFET we have in a device. One is called NMOS, one is called PMOS. Okay, so the NMOS stands for it's N-type. N-type MOS. So PMOS stands for P-type MOS. So which means there are some minor differences in the materials that are in these devices. So let's take a look at the N-type MOS first. If we have a cross-sectional view for this device, we are going to see something like this. Here is a gate, here is a drain, here is a source. All right, there are metal contacts. Here's a metal, and in the middle is the oxide material. So this is gate, this is drain, this is source. All right, and underneath it, that's N-type doping. So which means you mix with so here's the material is actually a silicon, but treated with some kind of other materials to make it semiconductor. So for the entire silicon, they dope boron in there to make it into a P-type silicon. And for here, they dope, or they usually use a heated process or high pressure to dope that material into there to make it not a pure silicon but a semiconductor. So here, the N-type, they mix the silicon with phosphorus. Let me see if I phosphorus in here. Okay, here is, so this is P-type, this is N-type, and they have a metal contactor here, have another wire which is called B, right? That's a bulk or the body contact. And so here's that's a cross-sectional view of the, it's called NMOS. So the reason this one is NMOS is because of the N-type material at the drain and the source, right? That's why it's an NMOS transistor. And when you apply a voltage, so before you do anything, there's nothing, no current flows through the transistor. There's just like, it's static, okay? Nothing is gonna happen there. However, if you, for example, if I ground source and I have a voltage source being connected to the gate and ground it here, and then I give a pressure, just a voltage pressure to the drain, then there's something gonna happen here, right? So the gate, if you have a higher potential at the gate, because here is positive, right? So electrons will be attracted from here to the channel. Okay, so after that, after the channel was being formed, if you apply a pressure to the drain and there are electrons, so the electrons will be attracted to this voltage source and flow into ground and make a voltage circle here. So you'll form a circuit. So electrons will be attracted to this voltage source and then form a circuit here. Okay, it looks like there is a current flow through that direction. So you get a current flow through that. And so the voltage at the gate has to be bigger. So for example, we call this G, here's S. So VGS has to be bigger than a threshold voltage. We call it VTH, V threshold voltage for the NMOS transistor. To make that happen, which means VGS has to be bigger than a certain threshold voltage, which depends on the fabrication process of the NMOS, to form a channel which is big enough to allow this pressure to push and have to form a current through that channel. Okay? And there's a IV curve which defines the voltage and current property for this device, which are pretty important. And we do not know too much about this, since all these current and voltages are in the continuous version are being covered in the analog electronics. If you are taking that course in the future, you'll learn a lot how to use, how to adjust the width and length of the transistor to make op-amp or to make ADC, so all these kinds of analog circuits. However, for here, we only need to know how that works, and we just use them to make up digital gates. That's it. Okay, there's no analog stuff. No too much analog stuff there. So for the NMOS, there's the IV curve, and the symbol for the NMOS is like this. Okay, here is a drain, here's a source, here's a gate, and you have another contact here, which is a body contact or bulk contact. So there's actually 4 terminals. And if you look at the cross section, so the symbol is actually being designed in that way. If you look at this, people just draw the symbol like that. So here's B, here's G, here's D, here's S. Right? Just look like in that way. D gate DGS B, DGSB. Right? So you have a DGSB, but we just draw it in another direction. And for this little transistor, if we apply a voltage to it, right, voltage here, and we ground this source, and we provide another voltage here. So this voltage, because it's grounded here, so they are sharing the same ground, and we can say that the voltage across these two terminals is the same as the voltage here. So here's the voltage, we can call it VDS. So we can name this voltage source as VDS. And the same thing here. This voltage source defines the voltage across G and S. So we call this voltage VGS, right? So if we keep VDS at a certain level, for example, 2 volts or something, as long as the pressure is enough to push the current go through that channel. And when we are changing the VGS as an axis here, and we can see what is the IDS, which is a current flow through the channel, will look like. That's IDS. So in the beginning, there's nothing. And after VGS is bigger than the threshold voltage, you will be able to see a current will increase exponentially, like that. But finally, it's going to saturate, anyway. But we usually don't draw this part. But we just care about this part, okay? And if you do it in another way, So VDS is fixed, right? How to spell that? Fixed, I think, is fixed. Then you can see this curve. However, if VGS is fixed, so which means it's not being changed. However, you are changing VDS and looking at IDS, the curve looks like this, right? It's saturated at some point. So these are the two main curves you need to remember. But why? You know, what's the intuitive way? Like you can understand this in a better way. So you may be able to think about the transistor just like a switch, okay, the switch of the faucet. So everybody's familiar with a faucet here, right? And there's a pump, which is giving a pressure to the faucet. So here's a gate. For example, that's a VGS of the transistor. So if you if you just define the VDS, which is, you know, let's say VDS is a pump, VGS is a switch, the knob here of the faucet, right? So if you just make the VDS, just make the pump at a constant pressure, and when you are increasing, when you are trying to turn the knob, so the water, you will see the water which is coming out from here, it's going to be, otherwise that won't be linear, because when you are turning that, it's trying to give a more capability of the pipe in the faucet to give you more water. It's going to like this, you'll turn on more and more from the beginning, right? After a threshold voltage, after a certain number of turns. For here, it's the same thing. If you have the turns on the knob is a constant, which means you have a certain width here for the faucet to allow the water go through, and you are trying to pump water into that faucet. It's going to saturate at some point because, you know, you have a limitation of the width of the pipe, so it cannot get too much water. But in the beginning, you will see a sharp increase, but finally it's going to saturate because of the limitation of the pipe. All right. So hopefully this will help a little bit. But however, these are not too many curves, just two types of curves. One is VGS versus IDS. One is VDS versus IDS. Just keep in mind, you know, these two curves looks different, and we can verify that using a simulation tool. I'm going to introduce you really soon. So that will be a better way to understand this as well. So this is IV curve for the NMOS, and we're going to take a look at the IV curve for the PMOS as well. So which is a complementary part to form a CMOS logic, right? Remember that CMOS is a complementary MOSFET, and one is NMOS, another one is a PMOS. So PMOS, similarly, instead of having NMOS, so N-type semiconductor material over here, you should have a P-type material. Here's a cross-sectional view. Definitely you have a metal here. That's a gate. And here is a source. Here is a drain. And you have a P-type. And you have something different, which is called N-well. It's a well, but adapted with N-type material. And you still have the same P-type substrate, same as NMOS. So why is that? Because we are fabricating a CMOS or semiconductor material on the same wafer, right? When people are fabricating their chips, they have NMOS, they have PMOS. It's not 3D. This is a 2D wafer. You have a wafer, for example, here, as a cross-sectional view. And you can have many NMOS and PMOS to be fabricated on the same substrate, right? So here's the NMOS, and here's the PMOS. But you have a P-type substrate, they're sharing the same substrate. So here's the problem. If you have a P-dot terminal here for source or drain, but you have a P-type substrate as well, you are making these two parts shorted. So all the currents will be shorted to the ground, which is really bad, right? You don't want that to happen. So the PMOS won't work properly. So what people did is people make an N-type well to accommodate all these P-type terminals in the PMOS. So you form a, here it's a different material, so they won't get shorted anymore because you have an N well here to insulate the P-type terminal to the P-type substrate. Okay, and people usually have a N-type contact to connect the things to the substrate, right? So this is how people usually fabricate PMOS in the same substrate with the NMOS. Okay, so now let's take a look at the PMOS. And the way we make current flow through the channel is when people connect the source to a higher voltage. You have a voltage source here, here, and for example, we ground the drain. Okay, and we have to connect the N well to the highest potential. But let's talk about this later. Don't worry about that. And so now, because compared to the source terminal here, the gate is relatively negative. You can see here is connected to the negative part of the voltage source. Here is connected to the positive part of the voltage source. So the negative part is going to start attract holes, which are, you can consider them as positive charges over there. And when there's another voltage being applied to the source, trying to push these positive charges to the drain, you are going to see a current flow through the channel. Okay, so that's how you can make a switch. You make the gate negative enough to turn on to form a channel filled with holes or positive charges, and then you give a pressure to the source, and you form a circuit here because they are both grounded. So the charges will flow through that circuit and come back to the negative terminal to the battery. Okay, this is how that PMOS can work. And the symbol for the PMOS looks like this. And you have a source, you have a drain, you have a gate. And also you have a contact which is being connected to the N well, which is the highest potential in the circuit. All right. So now let's take a look at the IV curves for PMOS. Yeah, so it's not an analog class, so probably this can be tricky, and we don't have too much time to cover too many things for the CMOS circuits in the analog part, because it's not analog class. However, we just trying to let you guys know as much as possible so you guys can still make logic gates out of CMOS transistors. We don't need to care about the IV curves too much. As long as we can, you just need to know how to turn it on, how to turn it off, which is actually super simple. So if you have a PMOS like this, that's drain, right? The way we're gonna turn it on is we want to make VSG is bigger than VTHP. All right, so that's the threshold voltage for the PMOS. We're gonna make a VSG bigger than that in order to turn it on. And now we also need a voltage source to give a pressure to it. So this is called VSD because it's connecting S and D, right? And the substrate of the PMOS, which is the N-well, need to be connected to the highest potential of the circuit. So this is how we connect everything in the PMOS. And of course, PMOS also have a pretty similar IV curve, but the voltages here is going to be VSG, and here is going to be ISD. When VSG is higher than the VTHP, you'll see a current flow through the channel from top to bottom, and it's going to increase exponentially. Similarly, if you have VSD increase and you have a ISD increase in this pattern and finally saturate at some value, pretty similar to the NMOS. So to convince you guys further, what I'm thinking is it's better to simulate both NMOS and PMOS in a simulation file. So in the same time, I can train you guys how to use it, since we are going to use this simulation software a lot in the semester. So I think we can probably start with another video, and we can have a LT Spice tutorial over there to show you guys how to use it and how to make the first simulation example in LT Spice for the NMOS and PMOS to get IV curves. All right, let's stop here, and I'm gonna see you in the next video.